So let's talk about kind of another way we can use the normal distribution and standard deviation. So as a reminder, although if you haven't watched the video on sort of the normal curve and standard deviations, go watch that one first. But as a reminder, we have S as our standard deviation. If this is our nice, beautiful bell curve, which is the normal distribution, then mean, median, and mode will all be at this peak. And so this is our mean, and just would also happen to be the median and the mode. But we would say then that the numbers under the curve here are standard deviations. So they are the distance from the mean. So half of the cases of our population are going to fall under on one side of the mean and half on the other. And so also sort of remember that within one standard deviation, you have about 68% of cases. Within two, and that means between -1 and +1. Between -2 and +2, you have about 95% of cases. And between -3 and +3 standard deviations, you have about 99%, or actually like almost 100%, but we just don't say 100%. So how can we use the normal curve and standard deviations when we're looking at individual scores? So an individual score can be given a position on that normal curve. So essentially what this means is that a person, an individual, will be given a score that's relative to the group mean. So where do you stand relative to the mean of the group that you're a part of? And so essentially, this is how things are standardized. And this allows for comparison across everybody who's in that population that we're trying to talk about. When we standardize it, then we say, well, if you are this far from the mean, then you are, you're above the mean or you're below the mean, and you're like really higher than most people or really lower than most people or right around where most people are. And that can sort of tell you where an individual sits in comparison to everybody else. So this concept is called standard scores, or much more commonly, we say that they are Z-scores. Of course, that is me being Canadian. I'm going to call them Z-scores. You guys can call them Z-scores if you want to, but I will always call them Z-scores. But essentially, this means that we're making a comparison between different distributions. So for example, we're looking at different scores on tests in different classes can then be standardized and compared. Hence, we're talking about standardization. So making it so that we have different sample distributions, and we can sort of combine them all and say, well, overall, here is the mean, and so here's where you fit compared to everybody else, even people who weren't part of the original group that you are a part of. So if we can look at, well, this is how this class did on this test, and this is how this class did, and you can see, well, where you fit regardless of which class you were in, for an example. So let's talk Z-scores. So Z-scores then are used to compare the relative position of an individual in either a group or within multiple groups. And so essentially a Z-score expresses the deviation of a score from the mean in terms of S. So it basically says how many standard deviations away from the mean are you? And are you above the mean or are you below the mean? And how far away from the mean are you? So that Z-score is going to be your how many standard deviations away from the mean are you? So some common uses for Z-scores, of course, they are used for standardized tests. This is how standardized tests get those, percentiles and tell you that you're in the 90th percentile or whatever for your SATs or any other standardized test. That's where these come from. And so that's why I have my little example here, where only in math problems can you buy 60 cantaloupes and no one asks what the hell's wrong with you. Because those are the kinds of questions you see on like SATs and stuff. But any standardized test, they're using Z-scores. That's what they're using. And essentially, it's useful in judging the rarity of any particular score. So if, for example, you are in like the 95th percentile, that means you are 2 standard deviations above the mean. And so your Z-score would be 2. So, I mean, that's not what you're given. You're told the percentile, but this is kind of where it's coming from. And so being 3 standard deviations above the mean or 3 standard deviations below the mean is very rare compared to being 1 or less than 1 standard deviation above or below the mean. That's a very common place to be. So your Z-score then will tell you how rare your individual score is compared to the overall mean and sort of the rest of the people. So here's what the formula looks like. It's a pretty simple formula. Essentially what it is you have your, and here's sort of written out in words, you have your distance of a score. So the score, so this is this person's individual score is here from the mean. So X bar is always the mean, same as when we saw it in standard deviation, the standard deviation formula. So it's the distance of the individual score from the mean, and then in terms of, so divided by the group's standard deviation. Pretty simple stuff. So you're seeing how far are you from the mean in terms of how many standard deviations. So just subtracting the score from the mean is going to tell you how far your raw score is from the mean, but we want to know how many standard deviations away you are, and that's why we're dividing by the standard deviation. So the result then is going to be a score expressed in standard deviations. So you are 1 standard deviation above the mean, or 1.5 standard deviations below the mean, or wherever you end up. So let's do an example. So we have 5 students. We have student A, student B, student C, student D, and student E. So these are their raw grades that they got on whatever test. Who cares? It's some test. So student A got a 90%, student B got a 90%, student C got a 75%, student D got a 60%, and student E got a 50%. So then these are, you can't really see the bar, but these are the X bars. So these are the means for basically the group of people that took that same test. So the mean for this test that student A took was 80%. The mean for the one student B took was 60%, etc. Here's the standard deviation, and here are the Z scores. So because we look at this, and so for example, this first one, if student A got 90%, and the mean is 80%. So then you subtract 80 from 90, that gives you 10. And then you divide it by 5, it gives you 2. So that's a Z score of positive 2. Then we look at student B, also got a 90%. The X bar, the mean is 60. So that difference now, when we say X minus X bar is now 30, divided by the standard deviation of 10. So it's also a little bit more spread out. And so then that person is 3 standard deviations above the mean. Comparatively, let's take this one down here, student D. So they got 60%, and so now that's lower than the average. So right away, before we do anything, we should know that because it's lower than the average, then it's going to be a negative Z score, because you know you're below the mean. So 60 minus 75 then is minus 15. So then negative 15 over a standard deviation of 15 is going to give you 1. So that means that this person is 1 standard deviation below the mean. And here's an example where it doesn't come out to a perfect number. Well, still pretty simple, but you have this person got a 50%, but the mean was 20%. So they are actually, even though they got the lowest out of all these 5, if we just looked at the raw grades, they are still above the mean. They're actually above it significantly by 30. And so this had a pretty wide spread of 20, a standard deviation of 20. And so that gives us a Z score of 1.5. So even though this person only got 50%, they are actually 1.5 standard deviations above the mean with that score. So this kind of gives us more information about sort of the relativity of what these raw grades mean. So the raw grades alone don't tell us as much as if we say, well, what is that grade in comparison to everybody else who took that same test? So for example, we say, well, who has the best score relative to the other scores in the group? We don't look at the raw grades, because the raw grades, we'd say, well, student A or student B did the best. No, but when we look at how it's relative to the other scores in the group, we actually then look at the Z score. So it's actually student B that did the best, because they got 3 standard deviations above the mean, because that mean was relatively low at 60 and they got a 90. So that they did really well. And then who has the worst? It's not this person with the 50, it's actually this person with the 60, because they are 1 standard deviation below the mean. So they are the one who has the worst score relative to the other scores. And So this other person who got 90 did pretty well. They're 2 standard deviations above the mean as well. But then this person who got the 50 is actually third highest. And so they actually are right in the middle in terms of how well they did compared to these other 4 students. So you can tell, this sort of shows you how the raw grade is not kind of good enough on its own if you really want to know, well, like, was it like a really hard test where like the mean is 20% and you got 50%, then you did pretty good, especially if it's a really wide spread. But it kind of gives you more information, and it's not just, well, you got 90%, but if like everybody got 100%, then you get 90%, you're actually doing pretty poorly. So in relative to the group. So this is basically what Z-scores do, is it puts those individual scores relative to what the group has been doing, and then it gives you a better indication of kind of where that person sits in terms of where the rest of the group sits, and sort of how everybody did.